Today we talk about colorings of the hypercube, and so I teach twice today. So this lecture and another lecture at, what time is it? 2 p.m.? So the usual David slot, I will teach again in that slot. So in this lecture, I want to discuss colorings of the hypercube, and in the next lecture, I want to discuss the proof of the first continuum lemma. So that's our plan. And so colorings of the hypercube, but as I said a few lectures ago, these colorings doesn't have to be colorings. They can be more general graph homomorphisms. And this hypercube doesn't have to be the hypercube. It can be some more general weak expanders. But to keep our exposition simpler, let's stick to the colorings of the hypercube. So for today's lecture, we define some notation. We'll use CQ of G. This is the collection of Q colorings. Here, Q colorings, a Q coloring means a proper vertex coloring with Q colors. Q colorings of the vertex set of G, and then we are going to use CQ of G. This is the number of Q colorings of the graph G. So this is our notation, and our today's model theorem is this. So we are curious about what's the number of 4 colorings of the hypercube. And this is known, so this is asymptotically equal to 6 times e times 2 to the n. Whether this, is this visible or is my handwriting too small? Too small? Oh, okay. So here, this n is the number of vertices, and so this is 2 to the d. So here, let me read this for you. C for QD is asymptotic to 6 times e times 2 to the n. Okay? Okay, and as we have discussed several times, what we have on the right-hand side is actually asymptotic lower bound. And as a starter of today's lecture, I want to discuss why we have this as an asymptotic lower bound. And this shouldn't be very different from what we have seen so far. So let's discuss that first. And first of all, I want to say that this 2 to the n, this is a really trivial lower bound on the number of 4 colorings of the hypercube, or on the number of 4 colorings of any bipartite graph. Why is that? Yeah? Okay, so slow down. So let's say this is our bipartition, and let's say this is O and this is E, and then?
So just choose 2 colors to be in O and choose 1 subset of O to have 1 of the colors, and the rest of them have the other colors. Okay,
great, wonderful. Yes, indeed, let's say our colors are 1, 2, 3, 4. And then we just pick 2 colors, let's say 1, 2, and then assign those colors here on one side, and then assign the other colors on the other side. And then just color the vertices, the even vertices with the color either 1 or 2, and color odd vertices with colors either 3 or 4. Then it can never conflict. It always gives a proper coloring, so this way we have the trivial lower bound 2 to the n. And then why do we have this extra factor? And we know answer. I mean, you know answer if you came to the if you came to the problem session. We have seen this before, but let me explain. So to get some extra factors, what we do is to plant noises. And so for now, let me just call them a ground state for our further discussion, ground state. And then what we do is we plant some non-nearby flaws. So like here, here. And then what does it mean by a flaw? That means the color of this vertex does not observe the color assignment for the ground state. So for example, for this vertex, can have color either 1 or 2. Okay, and then once we plant a flaw, and let's say the color of this vertex is 1, then what happens to its neighborhood? Its neighborhood originally had 2 color choices, 1 or 2, but now it loses one of the 2 color choices. Now, so they must be all monochromatic, and from there, we have some penalty. So we have to pay something to plant the flaws, but as a return, we have the penalty from the boundary of the planted flaw. So this is the usual thing. But if you still remember what happened for the independence account, there what we had was I of g is asymptotic to 2 times root e times 2 to the n over 2. So one big difference is, of course, there are many differences. 6 and 2 are different. One big difference is here we have e, but here we have root e. And the reason for that is because, so again, many of you have seen this before in the problem session. The reason for that is, unlike this independence account, for the coloring count, we have flaws on both sides, right? So it's possible that flaws are on this side, but it's also possible that flaws are on the other side. And in this case, this one is like 3, because this is a flaw, and then it also freezes the color of its neighborhood. So then what's the number of colorings with, oh, this is too small for you, maybe. The number of colorings with k non-nearby, let me just say non-nearby flaws. So what is this? We have computed this before. So first of all, we want to plant the flaws, and the number of choices for that is n choose k. So in the independence account, we had n over 2 here, but now we have n, okay? And times, we have 2 to the n minus the neighborhood of the size of the flaws, so we have this, okay? So this means everybody, like this n means everybody but the flaw, the neighborhood of the flaws has 2 choices, but the neighborhood of the flaws, they do not have any choices. Okay, and then if you simplify this, then we have n to the k divided by k factorial times 2 to the n minus dk. Let me speed up because you have seen this before. So this one and this one cancels out, so we have 2 to the n, 1 over k factorial, and if you sum them up, then this gives us e times 2 to the n. Are we okay? So this is boring now, right? Because you're an expert. Okay, and then why do we have 6 here? Because 6 is 4 choose 2. Okay, so there are 4 choose 2 many ways to pick our ground state. So that gives us 6 times e times 2 to the n. So are we happy with this so far? Question?
Don't we have to choose which colors the flaws are? I guess why is that already accounted for?
Oh, okay, so that is already addressed here. So this is only for the neighborhood. Yes, great, you're following, great. Any other questions? Yes? Oh, yeah, that is already addressed in 4 choose 2. So for
4 times 3, not 4 choose 2. Like, shouldn't the choice of the 2 colors be ordered?
I don't understand. So are you convinced? Oh, okay, thank you. Okay, any other questions? Can we continue? Okay, great, so far it was easy, and so you're following. And great. I apologize for the last lecture. It was pretty technical. And, but let's make it a little bit softer for today's lecture. Okay, and then for the next discussion, okay, so we give some names for those spatial colors. So we'll call this type of colorings, which means ground state with some non-nearby flaws, non-nearby singleton flaws. We'll call those colorings good colorings. And then what is a bad coloring? That is a coloring which is not good. So that's the definition for bad colorings. And our goal is to show that all of the bad colorings, the number of bad colorings is negligible, where negligible means it's little of this number. That's our goal. That's where we are heading to for today's lecture. Okay, so this is our goal. is the bad colorings are negligible. And of course, the proof of this statement is about like, at least more than 10 pages. So we cannot cover all of the details, but instead we'll discuss some special case and then to deliver what are the ideas to prove the statement like that. But before we move on, I want to make some comment. So this is for comparison. Many people asked what this means. So CF means comparison. For comparison, Jensen and Kivash extended this result for any Q coloring. So this result is due to my advisor, Jeff Kahn, and myself. And I think this was my first project when I was a graduate student. Anyways, after that, Jensen and Kivash, they generalized that statement and got sharp estimates for the number of Q colorings from the hypercube and or more general structures. But anyway, so what they proved contains the 6 coloring count for the hypercube. And they showed that this is 6 choose 3. You see where this comes from. Times 3 to the n. You see where this comes from. Times e. You see where this comes from. So, and then this is not the end. They show that actually the exponent of this number is something very big. 4 thirds times 2 to the d. And if we move further, if we are given 8 colors, then the situation is a little bit more complicated. So this is asymptotic to 8 choose 4. You know where this comes from. And 4 to the n times e to the 3 halves d plus something like this square, blah, blah, blah. Let me not give you the precise number, but I just wanted to emphasize that once we have many colors, then the asymptotics is not as simple as this thing. As you have more and more colors, the asymptotics or the number of colorings becomes more and more complicated. And this is pretty natural because as you have more colors, then the picture of our typical coloring gets more and more complicated. When you have small numbers, then mostly you see that mostly the vertices, I should write this way. The vertices are, so this part has color 1, 2, and this part has color 3, 4, and there are peacefully some small flaws far away from each other. This is what happens when you have small number of colors, but as you have many colors, then those flaws becomes more typical. So that ruins or that makes the asymptotics more complicated because the contribution of the picture with flaws becomes more typical, so they make bigger contribution. So this is what happens, but in this lecture, we want to make our lecture simple, so we'll just stick to Q to be a constant, and we will not consider Q, so we will not consider the situation where Q grows. So Q is always a constant. So we analyze a spatial case, and for that, I need a board space. So I think nothing important is written on the board, so let me clean up a little bit. So we analyzed the following spatial case, and this spatial case should be very familiar for you. So this is the problematic picture that we already discussed. So let me say this is revisited. And again, to keep our argument simple, we assume that Q, the number of colors, is always even, because in that case, we can equipartition this number. And so the picture is this. This is E, and this is O. And as a ground state, we assign colors from 1 to Q over 2 on one side, and then Q over 2 plus 1 to Q on the other side. And this coloring gives us, let me write here, this coloring gives us Q over 2 to the n. Many colors, many colorings. Okay, so that's gonna be our benchmark. Okay? And then what we do is we plant some flaws like this. You know what it means by flaws? That means those vertices have colors from the other. side. And then so let me call this flaw X, and then they have, and this is their neighborhood. And one big assumption that we have in this picture, just to simplify our argument, is that we'll assume that there are no flaws on the other side. So in the usual coloring, we have flaws on both sides. But in this argument, to simplify our proof, we assume that there are no flaws on the other side. And all of the flaws are on one side, and they are two linked. That's our assumption to simplify the proof. So again, X is two linked. We know what the definition of this is. And then the size of the closure, let's say this is X. And then the size of the neighborhood, let me say this is the worst possible case. So this is 1 plus some constant over d, root d, times x. So this is the usual setup. We'll just assume one simple, nice, clean case with the worst expansion. OK? And then my claim, or the goal of today's lecture, or maybe next lecture, is to show that the number of such colorings is much smaller than q over 2 to the n. And of course, here, much smaller means this is exponentially smaller than q over 2 to the n. This is our goal. And to show this, our driving force to achieve this will be, as usual, the penalty from the boundary. So we have to take advantage of the penalty from the boundary. Are we OK with the meaning of the word boundary? Boundary means the vertices that are adjacent to the flaws. So when you have this flaw set, like X, the boundary means like this part, the vertices that are adjacent to the flaw. This is what I meant by the boundary. Is the situation clear? OK. But before we actually start our discussion, I want to make a remark that this no flaw assumption makes the situation really simple. And this is really not the real problem. And the real problematic situation is where two flaws are adjacent. And let me explain why that is the real problem. So let me say, just to simplify the discussion, let's assume the Q is 4. So we have 4 colorings. And let me say the ground state is 1, 2 here and 3, 4 here. And let me say we have some flaws here. So their colors are 3 and 4. And as I said, the driving force for this statement is the penalty from the boundary. So if we have this vertex, then if this vertex is adjacent to 3 or 4, then this vertex immediately loses its color choice. So that causes the penalty. Then do you see why it's problematic that two flaws are adjacent? Do you see that? Because if we have this vertex, but this is a flaw, another flaw, and let's say this one has neighborhood inside another bigger flaw, that means now, because this one is a flaw, so the color choice for this vertex is either 1 or 2. And its neighborhood is 3 and 4. Is there any penalty? No. So the real problematic situation is when two flaws or when two flaws are adjacent, or we really do not have any control for the flaws on the other side. So I just want to say that this assumption is really big. And we're just taking care of this small toy example because this is a 1-hour lecture. OK? And also because I don't want to lose you anymore. So, say that again? Oh, OK, so here, so if we have a flaw, so OK, the driving force for this much smaller inequality is the penalty from the boundary. And this is because if we have a good vertex here, which is adjacent to a bad vertex, then this one loses its color. So from there, we gain some penalty. On the other hand, if we have a flaw here, which is adjacent to another flaw, then even if all of the neighbors of this vertex is 3, 4, which is against the ground state. If this vertex itself is also a flaw, then the color choice for this one is 1, 2, not 3, 4. So there's no conflict. There's no conflict between the color palette for this vertex, which is 1, 2, and the color palette for its neighborhood, which is 3, 4. So there's no flaw. There's no defect. What did I say? There is no penalty. Is this better? OK, good. Any other questions? OK. So then, where are we? Then I think I can erase this board. Is it OK? Because we need some board space. So this is our first try to prove that statement, and this will fail. So the first try, because we learned a fancy technique last time, which is called containers. So I want to use containers to take care of that, to achieve that goal. So let's use containers. And if you still remember the statement was the number of possible x's that satisfy this condition is at most 2 to the size of the neighborhood minus some exponential factor, minus some factor. So this is like, so I hide some log factors, and then this here we have the size of the neighborhood of x minus x. So we had something like this. Again, so here, if I hide this thing, then this is our benchmark. But by using some techniques by using container argument, we obtained this extra factor, which was really the driving force to prove the asymptotics for the number of independent sets. So this was very useful. So using this, we can give an upper bound on the number of Q colorings. But let me say number of such Q colorings, where such means the number of Q colorings that looks like this. Okay, and then what is this? This is at most, first we specify the flaws, and that gives us this number. So this is 2 to the neighborhood of x minus some term. Let me not write it down. So this is the cost for specifying the flaws at x. Once we specify x, now we color. We color this configuration. And for that is, I think I forgot to say n over 2. But we don't need to worry about it. We can just forget about it. And then we color the configuration, which costs q over 2 to the n minus the size of the neighborhood of x, right? And then, so because if you're not in the neighborhood of x, then you are free to choose any of the colors among the q over 2 colors. So this gives us this much. But then what happens if you're in the neighborhood of x? There can be some conflict. So from there, we lose some color choice. And in the worst case, what we have is q over 2 minus 1 to the size of the neighborhood of x. Because there is a conflict, that we'll lose one choice. We'll lose one choice or several choices. But in the worst case, we just lose one choice. So this is a worst case analysis. But on the other hand, there is no immediate way to improve this worst bound. Anyway, then what does this give us? First of all, this is our benchmark, so we can forget about it. And if you combine this thing and this thing, then altogether, what we have is 1 minus 2 over q to the size of the neighborhood of x. So do you think this is much smaller than this or not? Let me give you some time. So do you think this entire thing is much smaller than q over 2 to the n? Yes or no? There are two options. Who thinks yes?
The answer you said will fail.
Say that again?
You already put the answer that will fail, so no.
I don't understand.
You put the will fail.
Why I put what? What? At the very I will fail. Ah. Or not. Okay, so who thinks this is smaller than q over 2 to the n? Okay. Okay, do you think, okay, yes, no. What does it mean by yes? Okay, raise your hand if you think this is smaller than q over 2 to the n. Raise your hand if this thing is not smaller than q over 2 to the n. Raise your hand if you don't have any ideas.
Sorry, I'm super confused. So isn't the left-hand side just a number less than 1 and the other one like huge? Or
What is this one and what is the other one?
so the one that's 1 minus 2 over q, that's a number that's less than 1, no?
Yes, yeah, of course, yeah.
It's huge.
So this is like 0.9.
Yeah.
Uh-huh.
The right-hand side is huge. So isn't trivially the left-hand side smaller than the right-hand side?
Oh, but we have this.
Ah, okay, it's the whole thing. Ah.
Yes, yes,
Yeah.
yes, yes. Oh, okay, now I see that. So sorry, I confused you as always. Okay, so the entire, I meant the entire thing. Do you think the entire thing is smaller than q over 2 to the n or not? It's not. Do you see that? Because again, this is a benchmark. And here we have 2 to the n. Here we have, when q is large, so this is something smaller than close to 0.9. And so this 0.9, if you compare 2 and 0.9, you see that this is actually much larger than q over 2 to the n. Because we have 2 to the n and we have 0.9 to the n. Do you see that? So what is 2 times 0.9? It's 1.8. So what's on the left-hand side is like 1.8 to the n times q over 2 to the n, which is much bigger than q over 2 to the n. Please nod your head. Okay. Any questions? Yeah.
When q equals 4, is this strong enough to work?
That's a very nice question. Yes and no. Okay. So when q equals 4, yeah, in that case, this is okay. But as I said, this is not the real problematic situation. So because of this assumption, so yeah, it will not work. But you need to look at this problem more carefully to show that the proof doesn't go well. Great, great. Yeah. Any other questions? Okay. So the lesson that we get from this is this. So the lesson is that, oh no, this is expensive. When q is larger, then the penalty gets smaller. Do you agree with this? You see from here, as q gets larger, the penalty gets smaller and smaller. So in this sense, when q is larger, the container argument is too expensive. So we have to do something else. And for that, let me write down the fix that we can think about. So first of all, what plan are we implementing in the current approach? So the first container lemma that we discussed last time says that we can cheaply construct the containers. And we saw that this is pretty cheap, yeah. And the second lemma says that we can specify the flaws x from the containers. And this part was pretty expensive. And then, plus those two lemmas, what we are doing here is we apply the two container lemmas to specify x, and then we color the entire picture QD. So this is the plan that we implemented in this failed try. And then we just saw that this is too expensive. And in particular, what's expensive in this plan is this part is too expensive. And then from here, the intuition to fix the current approach, the intuition is this. Which part can I erase? I wish I could use the lower part of the board, then probably that's not good. Okay, So the intuition, believe it or not, if we consider bad colorings, then they also cluster. So we have seen this several times. First, we said independent sets cluster, and then we said expanding sets cluster, and now I'm claiming bad colorings also cluster. So again, believe it or not, at least maybe I don't know, but at least what we can do is, based on this intuition, maybe we can just skip the second part of the container lemma. So we skip the step that to specify the bad set X, and we specify colorings from the containers directly. So this is our plan. Again, in this previous plan, specifying X and then coloring, so doing this step in 2 steps is too expensive. So our plan is to skip the second lemma part and then specify colorings directly from the container. This is our plan. So, and to implement this idea, we need some formal setting. So let me write down some notations. I think I'll need the entire board. So let me erase this one. So this is our formal setting. The picture is as always. So we have this. This is E. No, this is O, E. And we have colors 1 to Q over 2, Q over 2 plus 1 to Q. And this is our flaw X. And this is the neighborhood of X. And there are no flaws on the other side. And then X is 2 linked. The size of the neighborhood, the size of the closure is A, and the size of the neighborhood is G. So this is a familiar setting that we used last time. And then we use C for the Q colorings whose flaws are like this. So in other words, C is the collection of this such Q colorings. The collection of Q colorings whose flaws satisfy this picture. That's the meaning of, that's the definition of C. Okay, C, so C is the collection of these spatial bad colorings. Okay, and then we'll use F for a member of C. So F is always a coloring, or is always a bad coloring. And then we use XF. This is a collection of flaws. This is a set of flaws of F. Okay? So once you are given a bad coloring, you look at its flaw, and that becomes XF. So this depends on F. Okay? And if we apply the first container lemma, it's okay if you don't remember the statement, because now I'm reminding you the statement. If we apply the first container lemma, then the containers whose name is SF. Again, don't worry if you don't remember this. I will give you a reminder. Anyway, what I want to say is finding containers for XF is cheap. That's what we discussed last time, and this is what we will prove in the next lecture. So this of the flaws, and this is cheap. And then for the rest of the lecture, we will not care about this cost because this is cheap. And then the claim. Is this. Given a container SF, the number of Fs in C, so the number of these spatial bad colorings, such that SF is its container, or the fancy word that we used last time is psi approximation, but if this is too hard, then you can just read it as a container. approximation of xf is much smaller than, I want to save some space. xf is much smaller than q over 2 to the n. So this is the claim that we want to prove for the rest of the lecture.
So does the psi approximation now depend on the color?
Oh no, so psi here, we can always think psi in this lecture is d to the 2/3. It doesn't depend on q. And also, remember, q is a constant. So it really doesn't matter. We don't care about constant factors. Okay, good. Any other questions? So final definition, we'll say a vertex is good if its color follows or observes the ground state. So if this the meaning of a good vertex is if this vertex is odd, then its color is 1 of 1 up to q over 2. And if that vertex is even, then its color is 1 of this to this. That's the meaning of a good vertex. So good vertex means it has a good color, the color from the ground state. Then what is a bad vertex? A vertex whose color is not in the ground state. Okay, great. Okay, so is it clear what we are proving? So we are given a container SF, and from there, we want to specify bad colorings whose flaw set, for which SF is its container. Yes? Oh, yeah, good question. Yes, a bad vertex is a flaw. Yes, you're right. Yes, sorry. Yeah. Okay, and probably we won't have enough time, but I can give you some wrong attempts. So as promised, let me give you a reminder of the properties of the container. So the container looks like this. This is our flaw set X, and this is our neighborhood. And the container consists of two parts. S contains the closure of X, and then F is contained in the neighborhood of X. And then there is some degree condition. So if you look at the degree of the vertices in S2 here, like df, then this is bigger than the 1 minus little o of d. And if you look at the vertices outside of F, and if you look at the degree in S, this is smaller than little o of d. Okay, this was the definition or properties of the containers, SNF. But in our picture, we do not see X and the neighborhood of X. We only see S and F and the degree condition. So given S and F, we want to specify the bad colorings for which SF is their container. Okay, that's what we do. And then first, let's think about some naive approach. So one naive approach is to color S and then color the rest, and see what goes wrong with this approach. So this is our picture, and then this is our S. And then we know that the ground state is like 1 to q over 2 and blah, blah, blah. Then let's say we pick a vertex from S. How many color choices does this vertex have? Without knowing anything, but this vertex is in S. So this vertex has this very wasteful cost, Q, because we don't know whether this vertex is good or bad. So this is the problem of the container approach, because we didn't specify X yet. Even if we have S, we don't know that this vertex is good or bad. So this vertex, if we do not do anything clever, then this vertex has exactly Q choices. So everybody has Q choices. And then let's color the rest. If you are not in the neighborhood of S, then we know that those vertices have Q over 2 choices, those vertices have Q over 2 choices, and then how about those vertices? Maybe in some case, maybe they have, instead of Q over 2, they have Q over 2 minus 1 choices. But this is never enough because our benchmark is Q over 2 to the n, and we already paid Q instead of Q over, do you hear me? Instead of Q over 2. So this part is already too expensive. Do you agree with this? So without doing anything, just color S first is not a good approach. Okay, so this failed. Then what else can we do? Maybe we can flip this approach and so color the rest first and then color S. Oh, no, I shouldn't erase this thing. Okay, maybe this one. So are you okay with the definition? Okay. So the second naive approach, maybe we can say we can color the rest of the vertices first and then color S. And let's see what's the problem. So this is our S. And if we color the rest of the vertices, all that we can do is to pay Q over 2 for each vertex, because we know that they're all good. So each of them has Q over 2 many choices, and there's no further information that we can take advantage of. And then, does this give us something good? Again, the problem is, if you're in S, then we never know this vertex is good or bad without any knowledge. Just by knowing that this vertex is in S, that doesn't give us any further information about this vertex. So the best thing that we can do is to look at its neighborhood. And then, get rid of those colors from our palette, and then, assign one of the rest of the colors to this vertex. And in that case, can we do something good? So again, if X is bad, then maybe looking at the neighborhood can be helpful. But if X is good, then again, we cannot avoid paying like Q over 2. For each vertex. Okay, so in this case, still, maybe we can achieve the bound something like Q over 2 to the n, but we cannot achieve much smaller than Q over 2 by using this approach. Is this convincing? If this is not convincing, then maybe you can prove it by pushing this approach. But okay, so here one lesson is, but at least looking at the neighborhood to choose the color of this vertex is helpful. And we learned a tool to push this idea. You're looking at the neighborhood and then decide the color of this vertex. And what tool was that? It starts with E. And then N. So what's the name of the tool? Entropy, great. And then you also discussed this yesterday in David's lecture. So we're going to use the method of entropy to take care of this bad situation. Okay? So far, it was more like an introduction to convince you why we want to use entropy. So let's do that. I keep looking for the eraser, but it's always at the end, on the opposite side. So where are we? Okay. Let me keep this picture. Okay, so to use entropy, we need a random variable, and our random variable is a uniformly random element of our bad set. So F is an element of C, and the choice is made uniformly at random. Uniformly at random. And if we do this, then what we can say is the entropy of F is exactly equal to the size of C. So our goal here is the same as this is smaller than n log Q over 2. This is our benchmark, minus something large. Let me not quantify what this large is, but you'll see what it is at the end. So that is our goal. Are we okay? So, and then to start from here, we have to make a decision, because we can use either this is entropy of Fe plus entropy of F O given Fe. This is one possible choice. But also we can do entropy of Fo plus entropy of Fe given Fo. So we have those two options. The first option says we reveal the even, so this is O and this is E. We reveal even vertices first, and then assign colors to the odd vertex. The second approach says that we reveal odd vertices first, and then assign colors to the even vertices. Which one do we prefer? Number 1 or number 2? Okay, so voting time again. Who wants to do the first one? Ooh, okay. Who wants to do the second one? Okay, who doesn't care? Nobody raised their hand? Okay, so there was somebody. Okay, I'll see you later. Okay, so is this already gone? So if you still remember, so I wrote down some comment at some point. What's the driving force of our approach? If you still remember that, what did I write down for the driving force of this approach? P from B. Yes, penalty from boundary. So we have to take advantage of the penalty from the boundary. And where is the boundary? E or O? E, right? And to use that penalty, I think it's better to open the colors in O first, and then leverage our information to get the penalty from E. So I would prefer the second approach. And actually, I tried the first approach, and then it didn't go well. But you can try if you raise your hand for that. Okay, so and for the reason for that is because the driving force is the penalty from the boundary. Okay, any questions so far? Because now we are jumping into more technical part. Yes?
So when you write F subscript set, that's the palette, right?
Ah, thank you so much. Yes, I should give you a reminder, and it's coming. So, okay, so this is not palette. This is a vector. Maybe I can give you the reminder now. So I used F sub A and F of A. F sub A is a vector, so it gives colors of all of individual vertices. So this is huge information. F of A is the palette. You just look at the colors that are used in A. So it gives a much smaller information. Okay, so those are the actual color assignment of the individual vertex. Okay, good. Any other questions? Okay, now we jump into the technical part. But don't worry, it's not as technical as the last lecture. So we use the second approach, and entropy of F is entropy of Fo plus entropy of Fe given Fo. And then using some techniques that we practiced, this can be bounded above by x in E, 1 over D, entropy of F sub neighborhood of X plus entropy of F sub X given F sub neighborhood of X. Do you believe this? So here I used various properties, and to get 1 over D, I applied Schur's lemma, and I used several properties of entropy. But are we okay with this? If you're not okay, then just believe this, and you'll have a chance to work it out in the problem session for a simpler question. So if you, okay, so do you believe this? Okay, great. So, and then our goal is to show that this is smaller than n times log q over 2 minus something large. So this is our goal. And because this term will be computed for each x, so let me give a name for this. Let me call this t of x. And then my goal is to bound t of x depending on where x is. Okay? So let me draw a picture. This is our S. This is our F. And this is our neighborhood of S. And then I partition E into 3 parts. The first part is here. And the second part is here. And the third part is here. And let me tell you what they are. So first of all, number 1, X is in E minus the neighborhood of S. In this case, I claim that T of X is at most 2 times log of Q over 2. This is very easy to see, so let me ask you, why is that true? Maybe I shouldn't have said very easy, a little bit easy. So.
We have Q over 2 options, right?
Yes, great. So if you are here, then X is good. And how about the neighborhood of X? They're also good. So that means each vertex in X and its neighborhood has just Q over 2 many choices. So we just pay log Q over 2 for each of them. And then, so because this is neighborhood, so this is summation y in the neighborhood of X, entropy of Fy. And then, this sum is divided by D. So at the end, we have 2 times log of Q over 2. Are we OK? OK. And then this is our benchmark. If we achieve this bound for everybody, then we'll have this, but not this. So our goal is to beat this bound using the properties of the containers. OK, number 2. What if y is in there? So the neighborhood of S minus F. In this case, OK, maybe it's helpful to give you some ideas. So in this case, the problem is, if y is here, then its neighborhood can be inside, not can be inside, it intersects with S. That means we have no idea whether the neighborhood of y is good or bad. It can be good, it can be bad, it can be a mixture, right? Because S contains some bad vertices. So in this case, we have to reveal the palette of the neighborhood first to get some information about the color of y and its neighborhood. So in this case, we expand T of y in this way. So this is at most 1 over D, entropy of F of n y, the neighborhood of y, plus 1 over D, entropy F and y, given F and y, plus entropy Fy, given the color of the neighborhood of this. Is this it? Yeah. But I think I need one more parenthesis and this. Is this OK? So we first reveal the palette of the neighborhood, and it has 1 over D because it's from this term. So there, what we use is that is equal to entropy of F of the palette. So I should use X here, plus entropy of F of F sub nx given the palette. We are just using this. So we can expand T of y in this way. Are we OK? What is this? Number. Maybe not number, expression. What is this? This is big O of some constant times. Oh, maybe I should have asked, what is this? So this is just a constant, right? Because palette has very small information. It's just constantly many choices. So this is constant that depends on Q, but Q is a constant, so let's not worry about that. So this entire thing is big O of 1 over D. Then how about this? So for this, we have to remember what we did, our discussion for the independent sets. So there, what we did was we look at y and we look at its neighborhood. What is the best place to write? So here, we look at y and we look at its neighborhood. and then consider several cases like when the neighborhood has, I don't know, okay. For now, let's assume the Q is 4, just to simplify the discussion. So in this case, the neighborhood can have like 3 colors or 2 colors or 1 color. And if the neighborhood has 3 colors, then the color choice left for Y is just 1, because we are with 4 colors. And then in this case, that one has 2. In this case, that one has 3 choices. And then what maximizes this expression? This expression is maximized when you have the equipartition of the colors. And in this case, this one is at most log 2 of log Q over 2. Because this expression is maximized when there are Q over 2 colors for the neighborhood, which leaves Q over 2 many colors for Y itself. And in that case, this expression is exactly log Q over 2. Not exactly, at most. Okay? So again, are we okay with this? Okay, so here, again, we were not able to beat the benchmark because it's possible that this achieves the maximum. Moreover, we have this extra term. So this is really a bad case because here our upper bound is actually even worse than this benchmark. So our last hope is to get some gain, get some penalty by considering the vertices in Z. And we don't have time now, so we'll continue this discussion in the second lecture.